Hi, my name is Vasishta, and this is my applications for thermodynamics and kinetics extra credit assignment. First, why standard delta S is negative for this reaction. In the balanced reaction, there are 4 moles of reactants and 2 moles of products. And since the number of moles decreased, standard delta S is negative because it measures the disorder, and having fewer moles means the system is less random because there's less microstates, which leads to a negative delta S. The sign of delta S surroundings is going to be positive because it's calculated using negative delta H standard over temperature. And it was given that standard delta H is negative since it's an exothermic reaction. And when you multiply negative by negative, you get a positive, obviously. And heat is added to the surroundings in an exothermic reaction, which increases the entropy, so it makes sense that the delta S of the surroundings is positive. The effect of increasing temperature on the equilibrium constant. Again, delta H is negative, meaning it's exothermic, and according to Le Chatelier's principle, increasing the temperature adds heat to the system. And since heat is a product, the equilibrium shifts left towards the reactants to absorb the heat and favors the reverse reaction. So KEQ decreases as temperature increases because the reactants are favored. The effect of the increasing temperature on the spontaneity of the forward reaction. So the Gibbs free energy is calculated with delta H standard minus temperature times standard delta S. And since delta H and delta S are both negative, as temperature increases, T delta S becomes more negative. So negative T delta S becomes more positive. Therefore, delta Gibbs energy becomes less negative as the temperature increases. So the spontaneity of the forward reaction decreases. Here's the graph for uh, standard delta G versus temperature for ammonia production. We found the slope and y-intercept of the line by converting the Gibbs free energy equation into y equals mx plus b format, and we plugged in the numbers. And here we have the y-intercept as delta H and equilibrium when delta G is 0. Anywhere where delta G is less than 0 is going to be a spontaneous reaction, and anywhere where it's greater than 0 is non-spontaneous. So as partial pressures of H2 and N2 increase, what direction will the reaction progress to maintain equilibrium? According to Le Chatelier's principle, increasing the partial pressure favors the side with fewer molecules, and since there are 4 moles of reactants and 2 moles of products, the reaction will progress forward to make more ammonia towards the products. Here, using the reaction quotient, we have the products over the reactants being nitrogen and hydrogen, and if the partial pressures of nitrogen and hydrogen increase, then Q decreases, making Q less than equilibrium, so the reaction will progress forward to reach equilibrium. When considering the delta G equals RT ln Q divided by K, if Q is less than K, then the natural log Q over K will be negative, making delta G negative, and the reaction will be spontaneous, which will drive the reaction forward. Why are the optimal conditions high temperatures and high pressures? Well, at high temperatures, molecules have more energy to help overcome the activation energy and break the triple bond in nitrogen gas. And at high pressures, the forward reaction is favored, which leads to higher ammonia formation. So the uncatalyzed activation energy, here we have the Arrhenius equation. And when you rearrange that into y equals mxb format by taking the natural log of both sides, you can relate it to the given equation. So the slope is going to be negative activation energy over R, which is going to be equal to negative 60,523. And when you solve for activation energy, you get 503,188.22. And then when you convert it into kilojoules, you get 503.18 kilojoules per mole. How the catalyst speeds up the reaction? Well, the catalyst creates a new reaction pathway that has a lower activation energy, which makes it easier for reactants to reach the transition state, and more molecules have enough energy to overcome this lower activation energy, so the rate of the reaction increases. How a catalyst would change the features of the plot from the previous slide is that the slope of the plot is negative EA over R. So if the EA decreases, then the slope will become less negative or less steep. Will this reaction proceed spontaneously in the forward or reverse direction to reach equilibrium? So first we have to find Q, and we do that by doing the pressure of the products divided by the pressure of the reactant, which gets us 0.0064. And since the equilibrium pressure is 0.00434, Q is greater than equilibrium, so there's too much product, so the reaction will proceed spontaneously in the reverse direction to reach equilibrium. To calculate the partial pressures of nitrogen and hydrogen at equilibrium, we have to set up an ice table. We have the initial pressures given in the previous slide, and we found that the reaction will proceed in the reverse direction. So we're adding to our reactants and subtracting from our products. And then we find the expression for equilibrium. We solve for X using the given partial pressure at equilibrium of ammonia. And then we plug that into our expressions to find the partial pressure of both nitrogen and hydrogen. Thank you.